Hello, welcome to truth tables. So here you're going to learn what logic gates and truth tables are and how to work them out mathematically. Right. So logic gates. Imagine you have a switch. In this scenario, we've got a push button switch, a piece of wire and a small bulb. When you close the circuit, electricity flows through and the light comes on. Now, a computer just contains millions and millions of switches, but obviously you can't press them all manually, so we need a different way of doing it. So we need some kind of digital switch. For that we use logic gates. What I've done here is I've added a very simple logic gate. It's an AND. Now you don't at the moment need to know what goes inside one. You just need to know how they work. So imagine now I've got two switches, push button switches again, connected to a battery. The first switch, nothing happens. I've got electricity coming in, but an AND gate will only allow electricity to flow out if both the first and the second input are switched on. And now you can see both are in, and the AND gate saying, fair enough, I will turn my output on. So that's a logic gate. It's a bit of circuitry, and an AND gate says when both my first and second inputs are switched on, my output will be on. And that's where the word AND is used in it. Okay. And there's different kinds. Here is a symbol for a buffer. A buffer is effectively like a piece of wire. And it's quite handy because electricity can only flow in one direction on them. But there's a few other advantages. Now, to work this out mathematically is quite complicated. So what we're going to do is we're going to give a symbol for the input rather than a switch, and a symbol for the output rather than a light bulb. And we're going to say that if the switch is off, then A, as you can see in the table there, is 0, and if the switch is on, then A will be 1. And similarly, if the output, if there's no electricity flowing, if it's off, then the Q in the table corresponding row will be 0, and the corresponding row will be 1. So this is a symbol for a buffer, and it's almost like a piece of wire. There are differences, but again, we can cover those later. Right, now, this looks like a buffer except for one big difference. We've got that circle there at the end. What that does is that inverts the answer. So as you can see on that table, if A is off, if A is 0, then the output is on. And if A is on, as you look in the table where it's a 1, then the output Q is off. And this will go for anything. So that circle around the end of that buffer inverts it, and so instead of a buffer we call this a NOT gate. So it takes an input and turns it back to front. Let's look at how that would work on our circuit. At the moment everything is switched off, so there is nothing going into the NOT gate, but it's pumping a signal out, so our light bulb is on. If we turn both of these switches, what then happens is both the first and second input are on, so the AND gate outputs an on with electricity. The NOT gate then turns it upside down, and an on becomes an off, and our light bulb goes off. So you can combine logic gates that way. Right, now to do these truth tables, there's some simple rules. A switch that is on is equal to 1, and a switch that is off is equal to 0. But we don't use switches, we use symbols for those switches, such as A, B, and C, and for the outputs, again, we use symbols, we don't use light bulbs, such as Q. When we make the table, we may have more than just one input, and in that case, what we do is we count up in binary, in the same way you learn to count in binary. Is 0, 0, 0, 1, 1, 0, and 1, 1, for example. So we tend to, although it's strictly not a hard and fast rule, you'll find that every truth table does that. So the inputs will be a binary that's counting up. Okay. So here's an example. This is an AND gate. And as you see on the truth table, it's only on if both A and B are on. So Q is the output, and for all other conditions, it's off. You may want to refer back to these slides later on when you're answering the homework. This is a NAND gate. So there's the circle. Let's come back to it. And it acts a bit like a NOT gate. So it is taking its... You notice that everything is off when both A and B are on, and for every other condition it's on. Okay. Right, so this is an OR gate. Now, an OR gate looks very similar to an AND gate. The difference is that where A and B connect, that's slightly concave. It's not straight. And it curves at the top and bottom, leading to the Q. So that's how you identify it, is a concave input, and it's more curved on the output. Okay, and if you look, an OR gate is on if any of the inputs, A or B, are on, or both even. That's an OR gate. Next one. A NOR gate. The same as an OR gate, but the Q, where it was a 0, has been turned to a 1, and where it was a 1 has been turned to a 0. So it's only on if both A and B are off. That's actually very different to a NAND gate. If you're not sure, look back at a NAND gate and you'll see that the truth tables are different. Okay, next one. This is an XOR. The X stands for exclusive. With this one, if A and B are on, the output is off, and you can see it's basically got that extra line added to the input which shows it's an exclusive relationship. So in the OR gate, when A and B were on, it was also on. Here, when A and B are on, it's off. That's the change between an XOR and an OR gate. And of course, if you add a circle to the end, then you reverse the Q, the output, and you get an XNOR gate, where it's only on if A and B are either both off or both on. Okay. Right, now you can combine gates as we did before. So what we've done here is I've taken my AND gate and I've combined it with a NOT gate. Now you notice in the truth table I've actually added the middle symbol, a Z. So you can see on the truth table that Z is only on when both A and B are on, but the Z then becomes the input to the NOT gate, and it turns it into a 1 where it was a 0, so we get it's only off when both A and B are on. And in fact, what you're looking at there is a NAND gate. So here's our NAND gate. They're both the same. They work exactly the same. So if you don't need to do the Z, then you can just draw it as a NAND gate, and you'll see that that's your truth table. Right. Here we've got a more complicated one. I've taken a NOR and an AND. Now, when I was talking about counting, now we've got 3 inputs, A, B, and C. And if you look, I've counted. So I start with 0, 0, 0, and then obviously 0, 0, 1, and so on and so forth. And it counts all the way up to 1, 1, 1. So it's counting in binary on A, B, and C. If you've forgotten that, please recap on the other presentation on counting. Now, I put the Z in so you can see. Now, you don't have to strictly put these in, but it makes it easier to see. And you can see here that the last 2 rows are both on. That's when A and B are both on at the same time. And effectively, you're then doing a NOR gate for Z and C. So if you now remember that what happens there is it will only be on the NOR gate if both Z and C are off. And you can see on the truth table there where Q is that only when both C and Z are off is the output on. Now, underneath I've written this mathematically. Use brackets all the time when you're writing these. So this makes it easier. So you can see here that A and B I've wrapped inside brackets, so you know that those two are ANDed together. Now I've put a NOR C, so the NOR is between the A and B bracket and the C itself. So that's how the inputs go. Your input will be either side of the gate when you write it. The difference is with a NOT gate. With a NOT gate there is only one input, so you would say not A or not B. So you wouldn't go A not. It's always the not comes first. But when you're combining inputs, then the inputs go either side of the gate. So A, then the name of the gate, and then the other input B. And I've used brackets to show that that itself is then one single output, which is being inputted into a NOR gate with a C, and that gives you Q. So you can often see the mathematical way it's written there.